Hello, this will be a demonstration of proposition 5 from book 4 of Euclid's Elements, which requires us to, about a given triangle, circumscribe a circle. We are given the triangle ABC, like so, ABC. And our task at hand is to circumscribe a circle about this given triangle ABC. We begin by bisecting AB at the point D and AC at the point E. We did this by proposition 110. Next, we draw these straight lines DF and EF perpendicular to AB and AC respectively. We do this by proposition 111, like so, and they'll meet at some point F. Now, this point F, the meeting point between the perpendicular bisectors of AB and AC, will either be within the triangle ABC, it'll be on the triangle, in this case on the straight line BC, or it will be outside the triangle entirely. First, if this point F be inside the triangle ABC, we join these straight lines AF, BF, and CF. We do this all by postulate 1. Now, we know that AD is equal to DB, and the angles ADF and BDF being right angles are equal. That's postulate 4. And we have the common side DF. So in the two triangles ADF and BDF, we have two sides equal to two sides, and the angle contained by the equal sides equal as well. And so these triangles here are equal in all respects, namely that AF be equal to BF. Similarly, we can show that, we can show that BF and CF are equal. This would involve saying that because AE is equal to EC, right, because AC is bisected at the point E, the angles at E being right angles are equal. Again, by postulate 4, we have the common side, the common side FE, and so these triangles are equal in all respects, again by 1, 4, so that we can say that that BF and CF are equal. And if AF and BF are equal, and BF and CF are equal, then it must be the case that AF and CF are equal. That's simple common notion 1. And from this point F, we have 3 equal straight lines. We have AF, BF, and FC, all coming from this point F. So by proposition 3.9, if we describe the circle with the center F and the distance FA, it will also pass through the points B and C. And so let's make this circle. We'll make this circle with the center F and the distance AF, BF, or CF. Like so. And this circle will be circumscribed about the triangle ABC, which means we have done what we set out to do. Next, let's deal with the case where the meeting of the perpendicular bisectors of AB and AC is on the straight line BC. So we'll deal with the case where, that's fine. Right? Like so this point F at which DF and EF meet is on the straight line BF or BC. And we can show in a similar manner that AF, BF, and FC are all equal to each other. We can show this again by multiple uses of proposition 1.4 and then a final use of common notion 1 to show that AF, BF, and FC are all equal, which means that again, from this point F, we have 3 equal straight lines, AF, BF, and FC, which means, again, by proposition 3.9, if we describe the circle with the center F and the distance FA, this circle will pass through the points B and C. So let's make this circle. We'll make this circle with the center F and the distance FA or FB or FC, it doesn't really matter since they're all equal to each other. And this circle will have been circumscribed about the given triangle ABC, which means we have done that which we set out to do. Finally, let's deal with the case where the the perpendicular bisectors of AB and AC meet outside the triangle. So look approximately like that. It's funny. Okay. And again, we'll join these straight lines AF, BF, and CF, like so. Do that by postulate 1. And again, by several uses of proposition 1.4 and common notion 1, we can show that AF, BF, and CF are all equal to each other, which means that the circle described with the center F and the distance FA will pass through the points B and C. This is again by proposition 3.9. So let's describe this circle with the center F and the distance FA or FB or FC. We'll make the circle ABC, and this circle ABC will have been circumscribed about the triangle ABC. And this is the final case which we have to deal with, which means that we have done in completion that which we set out to do. About the given triangle ABC, we have described the circle ABC such that it is circumscribed about the triangle. Now, there's another little corollary to this proposition. If the center of the circumcircle being the circle circumscribed about the triangle, if the center of this circle falls within the triangle, then this triangle will evidently be in a segment which is greater than a semicircle, which means that this angle right here will be an acute angle, which means that the triangle as a whole is an acute angle triangle. We know that this angle here is an acute angle by proposition 3.31, of course. And that angle being acute, the whole triangle has to be an acute triangle. Now, if the center of the circumcircle actually falls on the triangle, like so, if the center is right here, let's say, then we'll make that circle. If the center of the circumcircle is on the triangle, then this straight line here is evidently a diameter of the circumcircle, which means that this segment right here, which the triangle inhabits, is a semicircle, which means that this angle right here is a right angle. It's the angle in a semicircle, so it's a right angle. Again, that's proposition 3.31. And finally, if the center of the circumcircle fall outside the triangle, if it falls like here, let's say, and we draw the whole circumcircle, like so. If this center falls outside the triangle, then it is evident that this segment right here, in which we find the given triangle, this segment right here is less than a semicircle, which means that this angle right here is an obtuse angle, which means the triangle as a whole is an obtuse angle triangle. It's a neat little corollary to add to this proposition. And that being all I have to say about this proposition, proposition 4.5, I will end the video here and move on to 4.6.